Hi, my name is Dr. Felix Ndidi, affiliated to Department of Geography and Disaster Risk Management and Department of GIS, BEDC Electricity PSC, both in Nigeria. Before I proceed with this presentation, I want to first of all tender my apology for not participating in this um, program live. I had to do a recorded version because I will not be available to attend it fully, attend or participate fully. Uh, so I had to do this recording. I look forward to joining the forum in the future endeavor. Okay, the title of this research work is Anthropogenic Override and the Hydrological Non-Stationarity, Mapping Divergent Flood Regime in the Lower Niger-Benue Basin using HEC-RAS and remotely sensed data. This is a research work that has been completed and is currently being considered for publication in one of the Springer Nature journals. The Niger-Benue river basin in Nigeria, is Nigeria one of Nigeria's key agricultural um, and water resource zone, and it spans over 48,000 square kilometers across 6 states. Within it, Lokoja and Makodi, which is along the Niger River and Benue River respectively, are major urban hubs. Despite that both are suffering from seasonal flooding, long-term modeling emanating from this study um, shows that they operate under distinct hydrological systems. Recognizing these differences is essential to replace generic flood responses with tailored climate resilience policy and engineering solutions. However, in regulated river basin, the old assumption of stable flood pattern no longer holds because climate variability and human intervention interact in complex ways. Along the lower Niger-Benue river, human-driven factors like cross-border flow, dam release, and urban encroachment, urban floodplain encroachment, have disrupted the natural flood cycle. Using high-resolution FAB digital elevation model and roughly 3 decades of HEC-RAS simulation data from hydrological sensor, this study introduces a vulnerability to capacity metrics that shows how human actions have permanently reduced the natural floodplain capacity across the African river. Hence, the primary objective of this study is to determine the critical floodplain areas of the lower Niger-Benue Basin using hydraulic flood modeling approach. The research framework. This research is centered on using 2D and 1D hybrid HEC-RAS modeling approach, which was fed with 31 years hydrological or hydrological data captured with sensors on the river station, the river gauge stations, and also the FABDEM, which is was preferred because it removes forest and building biases from the elevation, and this was also used as data for the inundation model. Two other satellite images were used, such as the Moody's data. This was used in conjunction with the 31 years inundation annual peak flow data generated from HEC-RAS to validate the the model. Also, Sentinel-2 data was used to extract the true river path for the inundation model. The FAB digital elevation model also aided the extraction of the natural floodplain data, which also helped in the computation of the vulnerability to capacity index. The study area. The study area is basically focused on the Lokoja, that is River Niger, along the River Niger, and the Makurdi city along the Benue River. So the model was categorized into two based on these two major cities that have two hydrological different rivers. The study area has like I said, over 48,000 square kilometers, where the Niger River Basin, Niger-Benue Basin covers. The terrain is valid, ranging from 250 meters to 937 meters in elevation, with a broad floodplain, ridges, mesas, and undulating plain shaped by erosions. The region has a tropical savanna climate, distinct wet and dry season, and receive an average annual rainfall of 1,185 millimeters. Historical flooding event. The Niger-Benue Basin has endured frequent destructive floods since 1985, where this research we started facing the series of flood that has occurred historically. The Benue River is especially vulnerable due to excess discharges from the Ladgo Dam in Cameroon. Major floods such as the catastrophic 2012 event submerged over 13,700 square kilometers of land, displacing 1.3 million people, caused 431 deaths, and cost Nigeria an estimated 2.6 trillion naira in damage. More recent flood like the 2019 still displaced thousands and caused fatalities, underscoring the persistent threats to lives, properties, and agricultural land. The empirical results. After the model was done, it was validated using the precise recall and F1 score statistics. The Moody's data, which shows the historical flood event of the 2012, showing or rather displaying the true extent of the flooding. This extent was extracted from the Moody's data, and the flood inundation model from the HEC-RAS was superimposed on it. That is, the maximum flood was superimposed on it to compare the difference. And the HEC-RAS model, the particular date that correspond with the the 2012 October 2012 flooding events captured by the Moody's data was used, and that is what is presented here, where we have the over prediction through prediction of the two data. So the Moody's data was able to show that 94% of the time the HEC-RAS data or HEC-RAS model was accurate. The precision of 0.44 kilometers indicates that 94% of the area predicted as flooded were correct. Observed as flooded true positive, as shown in the map. The recall 0.93 indicates that the model captured 93% of the actual observed flood extent. The F core playing the part of the harmonic mean of the precision and the recall demonstrate a strong 94% balance between the classification accuracy and the completeness. Collectively, this high metric score confirm the robustness and stability of the HEC-RAS flood inundation models, suggesting a dependable predictive performance for the study. Okay, presented here is this spatiotemporal floodplain that was generated from the HEC-RAS model for the 31 years period that is being modeled. Each of these for Lokoja, this is for Lokoja, and this is for Makurdi. Each of these seem to capture the peak spatial flood extent or flooding extent at this particular location. The changes in flood frequency. The graph here shows a 31 years time series of the flood extent in the Lokoja model area, which is captured by the chart A, and it shows that the peak flooding year was 1998, marking the most severe inundation between 1995 and 2025. The overall trend indicates a decline in flooding magnitude and frequency over time. Three major flood peaks were identified, each exceeding 500 square kilometer inundation or submergence, occurring in the late 1990s, between 1997 and 2001, and mid 2010, captured between the 2012 and 2014, and around 2025, with roughly 10 years interval between the extreme events. This pattern suggests a decadal return period for major flood in the Lokoja floodplain. In the Makurdi model, which is captured by this chart B titled tag B, the flood extent analysis over this 31 years period shows the maximum peak flood peak occurring in 2012. Unlike the Lokoja trend, which revealed an upward trajectory that is increased, meaning flooding. Unlike this, the Lokoja trend, which shows downward trajectory. The Makurdi flood trend is showing an upward increase, meaning that flooding magnitude and frequency in this area is increasing over time. Temporarily, for the Lokoja model, the years with peak annual flooding are peak annual flooded area is temporarily for the Lokoja model, the years with peak annual flooded area greater than 457.56 square kilometer weighted average are considered high flood area or high flood year, while those years less than 457.56 kilometer square are considered low flood years. For Makurdi model, the years with peak annual flooded area greater than 179.1 square kilometer weighted average are classified as high flood years, while the years less than 179.1 square kilometers are considered as low flooding years. Regarding the flood frequency, which is captured in the table on this slide, the table shows that in the Lokoja area, there is an increase in the frequency of severe flooding since 2011. The early flood period, that is 1995 to 2010, on the one hand is dominated by low magnitude flooding, with 5 out of every 8 years exceeding the weighted average threshold. On the other hand, the recent flood period, 2011 to 2025, has shown a clear higher flood frequency, where almost half of all the years, that is 46.7%, have experienced flood extent above the weighted mean. Analyzing this data by flood frequency shows that the flood frequency of the years is falling below the higher magnitude, higher frequency threshold by 14.7%. This suggests that low years are being replaced by moderate magnitude flooding, moderate magnitude flooding events. That is, there is a shift in high magnitude flood frequency from about 1 in every 3 years to 1 in every 2 years, reducing the window of opportunity available for flooding disaster recovery in this area. This temporal partitioning provides a much more robust interpretation for the current flood management strategy in the Lokoja region and future hydrological planning than a simple linear trend or simple linear model. The frequency analysis for Makurdi clearly demonstrates a fundamental flood regime shift. Between 1995 and 2010, the early flood year, floods were mostly low to moderate in magnitude, accounting for 56.3% of the years, with high variability, and only 43.8% of the years reaching average or higher flood level. In contrast, the period from 2011 to 2025 shows a near near total dominance of high floods with 86.7% of the year exceeding um, the mean threshold and only 2 years falling below it. This indicates that the low flood years common in the late 1990s and the mid 2000s have virtually has virtually disappeared, and the system has transitioned from a variable magnitude regime to one characterized by consistently high frequency, high magnitude flooding. The natural and critical floodplain mapping. The vulnerability to capacity ratio was computed to quantify the proportion of the natural flood retaining area that is critically vulnerable. The use of the vulnerability capacity ratio um, uh, in this study seems to offer a powerful quantifiable metrics with high global utility that moves beyond standard exposure mapping. This manner of application is novel among global literatures. In Lokoja, as shown in Lokoja model, as shown in map A on top, and while Makodi is map B below. So that of Lokoja model map A, the vulnerability capacity ratio as captured in the table by the side um, is 0.565, meaning that about 57% of the natural floodplain area is critically um, um, vulnerable. Critically vulnerable. This indicates widespread exposure of the asset infrastructure, settlement, and farmlands with vulnerability dispersed across more than half of the Lokoja floodplain. By contrast, the Makodi model, that is model B, map B, shows a lower ratio of 0.365 or roughly 37% of its natural floodplain classified as critically vulnerable. This suggests that Makodi retains a higher relative residual capacity to absorb flood water before reaching the limit of its natural floodplain. Whereas Lokoja face a much greater degree of flood risk spread across its landscape. Okay, the key lessons learned. Because of the time I've spent, I think I've spent above the 15 minutes I was given. I itemized the key lessons learned and put them in full test for for our reading. Because of time, I think I'll just breeze through them. The key lesson learned is that flood vulnerability in Lokoja is widespread and severe, and Makodi floodplain behaves differently. All these are explained here um, uh, or captured here for our reading and further understanding. I'll just go to the recommendation, which I did same thing here. The first relates to the floodplain land zoning system. We're trying to recommend a floodplain land use system um, where we have 1 tier, 2 tier, and 3 tier, and the projection that we felt will um, help to mitigate this flood issue and the impact on our farmland settlement and infrastructures. I think the presentation ends here, though I'm not available to take questions and to uh, learn more from the discussion that we precede this presentation. I'll appreciate it if the questions are compiled and sent to me. I believe that I will also receive, if not a video discussion or the recording of the program to actually assist me in improving on this research work. Thank you very much, and I look forward to being physically active in future proceedings. Thank you.